So for FRQ2, we're going to write down the values that were given. So mass of the object moving along the x-axis is 4 kilograms, and its velocity at x equals 0, so v at 0, is equal to 6 meters per second. And this is the graph that we're given to work with. It's a graph of force over distance x. So we know that this, because of the values given here, we know that the area in between the x-axis and the curve of the graph will be the work done on the object by the force. So when the area is beneath the x-axis, it's going to be an opposing work against the motion of the force, and when it's above, it's going to be work that aids the object, like pushing it. So knowing this, for part A, it asks us to find the particle speed at x equals 2. So we're going to set up the equation first. So the speed, we're gonna use kinetic energy and work to find the velocity. So we know that Ke at 2 is equal to the kinetic energy as time. So this is telling you the distance. So kinetic energy when x equals 2 equals kinetic energy when x equals 0 plus the work done from 0 to 2. And if we break this down, we know that kinetic energy is 1/2 mv squared, which is v at 2, equals 1/2 mv at x equals 0 squared, plus work, as I said earlier, is the area in between the curve and the x-axis. So from 0 to 2, this area here is 10 or negative 10 because it's below the x-axis. So we can put that in as the value for work. And if we plug in all the numbers that we know, 1/2 m is 4, v2 is the unknown that we're trying to find, equals 1/2 m is 4, v at 0 is 6 squared, or plus a negative 10 for work. So what we want to isolate for v at 2, so we're going to divide both sides by 1/2 times 4, 1/2 times 4, and we're left with v at 2 squared equals, plug all of this here into a calculator, and we'll have 31, and the square root of 31 to find v2 is 5.56 meters per second is the velocity at x equals 2. And to find speed using velocity, it's just the absolute value of velocity. So speed at 2 is still positive 5.56 meters per second. And then for part B, asks us to find the time that it travels, the time of travel from x equals 0 to 2 meters. So we know we can use impulse here to find time, because impulse is equal to the change in momentum, which is mv final minus mv initial. And impulse is also equal to force times change in time. So we can set this to this. So it will be mv final minus mv initial equals force times change in time. And since it's asking for the impulse from 0 to 2, we already have all the numbers we need to have. Mass is 4, v final is v2, which we found earlier to be 5.56, minus mass again is 4, and v initial is 6, which is the given initial, equals the force here. The graph tells us from 0 to 2 is just -5, a constant. So we can plug in -5, change in t to find for, to solve for time, we divide both sides by -5. Plug everything here into a calculator and you'll get that time equals 0.352 seconds, which is the time it takes for the block to travel from 0 meters to 2 meters. And for part C, it says find the impulse experienced by the particle between 2 meters and 4 meters. So again, we're using this formula. Impulse is a change in momentum, which is v mv final minus mv initial, change in momentum. And the v final that we're trying to find is at the velocity at x equals 4 meters. So mv4 minus the initial that we're starting at is mv2, the impulse between 2 meters to 4 meters. So to find the velocity at 4, we're going to do k kinetic energy at x equals 4 is equal to kinetic energy at 0 plus the work done, the net work done from 0 to 4. So we're breaking that down into 1/2 mv4 squared equals 1/2 mv at 0 meters squared plus the work done from 0 to 4. Using the graph, we see that we're looking for the area from 0 to 4 here, so we know that this is 5, 15, and then half of 5 is 2.5. So it's going to be negative 17.5 is the area under the x-axis, which is the total work done. And this is opposing work because it's under the x-axis. So plugging in what we know, 1/2 m is mass is 4, velocity at x equals 4 meters is what we're trying to find, equals 1/2 m is 4. Velocity at 0 meters, is 6, which was a given earlier, squared, and the work done minus the work is 17.5. So to isolate for v at 4, we're going to divide both sides by 1/2 times 4. And v at 4 squared is equal to 27.25. A square root that to find v at 4 is 5.22 meters per second. So that's the velocity of the object at 4 meters. So we can go ahead and just plug that in. We know mass is 4 times the velocity at 4 is 5.22 minus the mass is 4. And we already found earlier in part A that the velocity at x equals 2 meters is 5.56. So we can plug that in, 5.56 meters per second. So impulse, plug all this into a calculator. Impulse is negative 1.4 newtons per meters, the unit for impulse. So that's the impulse from 2 meters to 4 meters. And then for part D, it asks us to do the same thing, except this time it wants us to find the impulse from 3 meters to 5 meters. So again, setting up the same thing, impulse equals mass final minus mass times v initial, which we know to be v final is going to be the v at 5 meters minus V initial is going to be the V at 3 meters. So to find V velocity at 5 meters, we're going to do the kinetic energy and work again. So KE at 5 equals KE at 0 plus the net work done from 0 to 5. Break that down into 1/2 mv squared. And the work, we know from 0 to 5 using the graph, is from 0 to 5 is 5, 10, 15, 17.5, and then this is a negative 17.5, and now we have to add a positive 2.5 because of this work done here at 5. So it's gonna, these two cancel out, so it's just gonna be negative 15 is the work done. And plugging in everything we know, 1/2 mass is 4, VF5 is what we're looking for, and V initial is 6 plus this negative 15 here. And we're isolating for VF5, so we divide both sides by 1/2 times 4. Plug all of this into a calculator, and then we have VF5 squared equals 28.505, and we square root that, and we have VF5 equals 5.339 meters per second. And so that's one of the velocities that we need for this equation. And now we're gonna find the second velocity, which is velocity at 3 meters. So again, the kinetic energy and work down, KE3 or KE kinetic energy at 3 meters is equal to kinetic energy at 0 meters plus the work done from 0 to 3 meters. So we know again that using the graph from 0 to 3 here, the work done is negative 15. The area between the two lines is a negative 15. So bringing that down, V3 squared equals 1/2 m V at 0 squared plus the work done is negative 15. So the numbers, plugging in the numbers we know, which is as we did earlier, dividing both sides by 1/2 times 4 to isolate for a velocity at 3 meters. Plugging all this into a calculator, we have velocity at 3 meters squared equals equals 28.5 again, and square root both sides. Velocity at 3 meters is equal to 5.339 meters per second. So we have velocity at 3 and velocity at 5. We can plug it into here. So we have impulse equals mass is 4, velocity at 5 equals 5.339 minus mass is 4, velocity at 3 is also 5.339. So we have impulse from 3 to 5, the block experiences is 0 newtons per meters. So that is part D. And then using another piece of paper because we ran out of room for the rest of the problem, we have part E asks us to find the particle speed at x equals 10. So again, using the kinetic energy and work theorem, we can find velocity at 10. So setting up the equation, kinetic energy at 10 meters is equal to the kinetic energy at 0 meters plus the net work done from 0 to 10 meters. So breaking that down, 1/2 m v at 10 squared equals 1/2 m v at 0 squared plus the work done. We'll look at the graph again. So we know here that these two will cancel out because they're the same values, just a negative and a positive. So we have a negative 15 here plus a positive from here to here is 25. So the work done is negative 15 plus 25. That's the total work. That's the net work done on the block from 0 to 10. So plugging in the numbers we know, mass is 4, V of 10 is what we're looking for. And again, mass is 4, V at 0 is 6 squared, plus negative 15 plus 25 is 10. So divide both sides by 1/2 times 4. We'll have V at 10 meters squared equals 41, and square root that. V at 10 equals 6.403 meters per second. And the speed of an object is just the absolute value of the velocity. So speed at 10 meters is still 6.403 meters per second. That's part E. And now we're going to do part F, which is asking us to find, does the particle turn around at some point and head back toward the origin? So the way that we know if an object is turning back is if the opposing work done is greater than the kinetic energy of the object, because that will mean that the opposing work is now forcing the object to move the other way. So we're trying to see if does at any point the work net work, is it greater than the kinetic energy? And in this case, we know that the only time that the work is opposing or negative is from 0 to 4. Past that point, the work is positive, so there's no point looking there, because we know that if it isn't already moving towards the origin here, then the work, it won't move, it won't be pushed back towards the origin, because this work is positive, pushing it in the direction it's already going. So we'll just look at the net work from 0 to 4 for this question. So using the graph from 0 to 4, and this is the kinetic energy at 0, because that is the velocity that we're starting out with. So from the work from 0 to 4 is, again, we found earlier already the area to be 17.5. So is 17.5 greater than the kinetic energy of the block at 0 meters? Plugging in mass is 4, which is a given, and the velocity at 0 is 6, which is also a given, which goes to be 0.5 times 4 times 6 squared. And here we'll see that 17.5 is not greater than 72. So we know that with a given initial velocity of 6 meters, the block, there would not be any point where the block heads back towards the origin, because the opposing work done won't be greater than the kinetic energy. So it asks us to repeat that part again in G, except now it's given that the initial velocity is 2 instead of 6. So again, we know it's the same constraint. We're looking at the negative opposing work from 0 to 4 meters only, which is the only time that it could possibly turn back towards the origin. So that's 17.5, as we already found up here. And is that greater than the kinetic energy at 0 meters when the initial velocity is given to be 2 meters per second? So 1/2 mass times velocity. Mass is 4. The velocity at 0 is now given to be 2. That's going to be 8. So the negative opposing force, 17.5, is greater than the kinetic energy. So at some point within this time here, the block will turn back towards the origin, because the opposing force is now greater than the kinetic energy, the initial kinetic energy. So that is it for FRQ2.